Okay, good morning, everyone. This is our lecture 5 about statistical hierarchical linear model class. So today we're going to continue our discussion and we're going to try to finish most of the materials we will cover for linear model. And then we'll move on to generalized linear model. So today, this is what we left from last class, the analysis of covariance. So what it means is that in the linear model, we have predictors that include both categorical predictors, which we call factors, and numerical predictors, which we would directly use their numerical values. So for illustration purpose, we just talk about two predictors, one as a factor, the other as a numerical predictor. So the numerical predictor is indicated by X, while the factor contains capital I levels. And we basically assume that in each level, the intercept is different. So each level contains Ni observations. Taking the sum, we have a total of N observations. That's our sample size. And whenever we have a factor, our notation for the Y, for the response, has two sub-indices. One is for the level, the other is for the number of observation or the observation index within the level. So this is our systematic structure, the linear part. So this is the mean for the response, and we write the mean as the common intercept for all levels, the specific intercept, the offset for level I, and this is the effect of the numerical predictor. And of course, in linear model, the random structure is always assumed to be normal. So the mean is the mean, and we have a common variance for all the observations. This is the ANCOVA model. So then the left question, the question we left for you in the last lecture is, how would you write out the design matrix? So the design matrix in this case, as we know for identifiability, we set the first level's offset to 0. So it means that we are left with I minus 1 offsets, right? So our beta parameter will be specified as the common intercept mu, offset of level 2 to offset of level I, and then the slope for the numerical vector. Or probably I should change the notation. Sorry, I think I changed that last time, gamma. And let's call it gamma. So you will have gamma as the slope, and the parameter beta is used for the whole coefficient vector to be consistent with our previous notation. So then to write down the vector form, that is, we need to write as y equals x beta plus epsilon, right? Then we need to know how the design matrix should be like. With that, we can just do a standard linear regression and we're done. So then for this design matrix, we know every column corresponds to one parameter. So this is the common intercept alpha 2, alpha I, and finally gamma. So the first column is obvious. It should all be ones. It's just the intercept. We have one for every observation. The last column corresponds to the numerical vector. So we will just write down its corresponding value. Of course, every row is corresponding to a row in Y, right? So since we are doing this factor or stratification based on the factor, we will lay out our response as Y11 to Y1N1. That's for level 1. And then YI1 to YINI. That's for level I. So that's my vector for the response. So the rows of X will correspond to the entries in the response. So therefore, in the gamma column for the numerical predictor, we have X11 to X1N1. And the last level, XI1, XINI. The other column corresponds to the levels each observation is in. So for the first N1 observations, they are all in level 1. So of course, they will be 0 in these columns. Okay, and oh, sorry, yeah, exactly. And then starting from x21 to x2n2, they will have ones in this column, right, corresponding to alpha 2, and 0 elsewhere. And for the last block, for level I, they would have 1 in these columns because they are in level I, and 0 elsewhere. So I would say that how to fill in the design matrix is the key for this part. If you understand this part, then you can use the standard R function Lm to solve any linear regression problem. Okay, so for this special case where we have one numerical predictor, one factor predictor, and in the systematic structure, we didn't assume any interaction between the two things. So what does this correspond to geometrically? It's actually corresponding to parallel lines. So let's call this as xij, observations in the numerical vector, and mu ij, okay? The expectation of yij in the systematic structure. So what this assumes is that we have parallel lines. So their slopes are all equal to gamma, and they only differ in their intercept. So you can imagine, so if I draw the lines to be this, then if I call this as mu, right? And then this one, I can call it mu plus alpha 2, and this is mu plus alpha 3. So their differences in intercept is what we call the offset, and that's the effect of the factor levels. So then you can imagine that this is a pretty strong constraint on the systematic structure. So for example, let me give you a concrete example for the factor. It could be your education level. And then let's say the numerical factor, the numerical predictor is the number of hours a person works per week. And then the response is the income per week. So if we assume this model, then what we mean is that given your education level, the number of hours have the same effects on the income. So that's what the slope is, the constant slope is referring to. But if you believe that this is not reasonable, then you can assume different levels give you different slopes, right? If we want to drop this parallel assumption, then we could change the slope to be level specific. So this is interaction. So it ANCOVA with interaction. So what we modify is the systematic structure. So previously we had this mu ij equals mu plus alpha I plus gamma xij. Now this common gamma would also involve some I to reflect the level. So we can change this to mu ij equal to mu plus alpha I. This is the intercept part. And for the slope part, we can write as gamma plus eta I xij. So you see this eta I part is the change in the slope imposed by level I. So of course, for identifiability issues, we always need to set the first level to have no effect. That is, we said alpha I equals eta I, alpha 1 equals eta 1 to 0. Okay, so then you can ask the question, what is the design matrix in this case? So clearly the design matrix will correspond to the parameters. The columns of a design matrix will correspond to parameters. So here we have mu, of course, alpha 2 to alpha I, right? And then this is the gamma. Okay, and we have eta 2 to eta I. Okay, the first few columns will be the same as before. What's trickier is for these last few columns we added for the interaction. What would be the corresponding values? So you see, basically eta I is going to be multiplied by xij if the I in xij is the same as the I in eta I. So it's only multiplied to observations of its level. So therefore, for the first ni columns, ni rows, for these observations, they would have 0 for these eta 2 to eta I columns because they are not in level 2 to I. But for the next n2 observations, they are going to have this eta 2 as an offset in the slope. So therefore, eta 2 is going to be multiplied by x2 something. So we will have x21 to x2 and 2 here for the second block. Okay, and finally, for the block I, right? They are for level I. So these things will have xi something in the last column. xi1 to xi and I. So you will only give the columns the corresponding observations in the same level. That's the key. So that's how the design matrix will look like for this part. So with this, you can still do multiple linear regression. Okay, so there are several questions you want to ask for yourself because clearly you are introducing more parameters and making the model more complex. Then you want to know whether it's worthwhile to do that. Then you can ask this question by using the wall test or the likelihood ratio test or hierarchical ANCOVA to test whether these etas are 0. Okay, so check if eta 2 to eta I are 0. And this is a hypothesis testing question. Right? And you have 3 options we have covered so far. The wall test, the likelihood ratio test, or the hierarchical ANCOVA. So this can help you decide whether you can stay with this parallel line model or this more complicated model. I'm just going to draw it. In this model, the lines could have different slopes. So you could have something like that. So different slopes for different levels. So this is a data fitting issue. You can always fit your data better using a more complicated model, but the improvement may be not so substantial. And in that case, if you run this test, you may not reject the null. So if you do not reject the null, you think, okay, there is not enough evidence to say I want to set this eta to be non-zero. So in that case, I want to just go to the simpler model.
Would there be like any difference like using the three tests, like difference in terms of power, or they're just equivalent?
I would say they're mostly very similar because there are slight differences whether you use the F-test or a chi-square test. But unless your sample size is very small, the F-test and the chi-square test will give you very similar p-values.
Okay. Thank you.
Okay, so that's all. So the next part before we conclude the linear model is the regression diagnostics. So in classic linear model, diagnostics is a very important part for you to trust the model results, the fitting results. So here is the general philosophy for doing model diagnostics. So we know that the model using a model to or probabilistic model to fit your data, it contains 3 stages, or I would say statistical modeling has 3 stages. So let's look at that first. 3 stages of statistical modeling. And this is what everyone does in applications. So the first question, the first stage is to formulate a model. So this is the part we have spent most efforts talking about, right? So this is a different formulation from this one. Then model formulation is your choices. You need to consider possible models you want to fit to your data. So specific to this linear model case, we need to consider 2 things. So first one is the randomness in the response in Y. So specifically here, we consider the randomness to be something that's not captured by the linear part of the model, right? The error term. So what we have talked so far is by assuming that Y is following a normal distribution around its mean. So that's the randomness we have assumed. But later we'll see that Y may follow other distribution given its mean. And the second thing is to, in the linear model part, is consider the systematic structure. The systematic structure is to link, basically to link the maybe I should say yi, link mu I to some predictors of observation I. This is what we call the linear part, right? We want to find or assume some relationship for each observation I between its expected response, we call mu I, and its predictor values. If we do not assume a systematic structure, like we said before, it becomes a saturated model. That is, each yi has its own mean, and we do not link the means of yi's in any way. So for that case, every mu I has only one observation yi, and we cannot do anything else. So the systematic structure is basically to tie the observation together to fit one model. This is the formulation part. And the second part is fit the model to data. So this is also what we call model parameter estimation. And in this class, the parameter estimation or the fitting is done by MLE, maximum likelihood estimation. This is what we use for this class. But as you learn more, you will see that for some models, it's very difficult to do MLE because its likelihood may not be a tractable mathematical function. So that applies to some modern models like the stochastic block model, those kind of things you can learn from other classes. So in that case, you have to approximate your likelihood to make it tractable, and then you maximize it. Or you have to use some other approaches to do parameter estimation. But in other words, this step is essentially an optimization problem, because you're trying to maximize the function. And as I said, optimization is becoming more and more difficult for those modern complex models. So that's why optimization, although it's not a traditional it's not in the traditional curriculum in statistics, but it has become more and more important for people doing statistics, machine learning. They want to know some optimization. Okay, once you have the parameter estimate, the last, if you want to use this model for prediction, okay, so if you want to make this model for prediction, or if you want to talk about the parameter inference, like whether a parameter is 0 or not by doing statistical testing, right? The inference is only meaningful if you trust your model, if you think this is a reasonable approximation of the truth. Then the last thing is to check the model. And this is what we call here, the diagnostics. We want to make sure that the model fitting results can retrospectively let us check our model assumptions and see, yeah, the model assumptions are not crazy. Okay, so now coming back to the special case of linear regression, well, how do we do model diagnostics? So for linear regression, the most important thing is to look at the residuals. And we know pretty much about the residual. If you recall, we rewrote it as y minus y hat. This is an n-dimensional vector. And this residual vector can be expressed as y minus x beta hat, right? And if you recall, beta hat by ordinary least squares has that special form, x transpose x inverse x transpose y. And we call this the hat matrix before. So therefore, the residual is identity minus hat matrix times y. That's what we have for the residual vector. And if you recall, we have derived that the residual vector has 0 mean. So its mean is an n-dimensional 0 vector, and its covariance matrix is sigma squared times I minus h. Okay, and this is an n by n symmetric matrix. The reason is of this form is that the H matrix is so special that it's idempotent, so its square is itself. And we also derived the trace for H, if you recall. So we have derived that the trace of H is just equal to P, the number of parameters in the model. And the idempotency of H has a very important implication. So this thing. What does it imply? So if you recall that matrix multiplication formula, this implies that for the, if we call the I diagonal entry of H by HII, then by the matrix multiplication formula, that H is equal to H squared, we can actually know that this is equal to, and also H transpose is equal to H. So given symmetric and idempotent, we would have that HII by matrix multiplication is actually equal to HIJ squared, because it should be equal to XIJ times should be equal to HIJ times HJI and summation over J. That's the matrix formula, multiplication formula. But now, since HJI equals HIJ by the symmetry, we have this. So what does this imply? If we expand the summation, it's equal to x11 squared plus 2 hi1 squared plus 2 hii squared plus HIN squared. So there are n terms here, and one of them is HII squared. And because we know every square term is non-negative, this is greater or equal than HII squared. So we have HII greater or equal than its square. And this tells us something very interesting. That is, HII is between 0 and 1. And we can show that HII is positive first. It's non-negative, sorry. It's non-negative first. And then we can use this, we can show that it's between 0 and 1. And this is something we must have, because if we check this variance formula, this covariance matrix formula tell me that if I look at one particular residual I, then that residual I's variance can be expressed as sigma squared times 1 minus HII, the I's diagonal entry of H matrix. And we know that the variance must be non-negative. So that can also tell me that my HII cannot be greater than 1. So this is very important thing to know. And also what this implies is that unlike our random error term, which we use epsilon to stand for in our linear model. So if you remember, in the model, we assume constant variance. So the variance of epsilon I is equal to sigma squared for every I. But in the residual, in the residuals, the variance of EI is equal to sigma squared 1 minus HII. And this implies that different residuals have different variances. So that's different from the random error term. Okay. Different residuals have different variances. And the variances would depend on the HII. That is the hat matrix. So now let's pause for a little time, and I want you to think about what does the variance of the residual mean in our notation. So when we say variance, we treat the residual as a random variable. Then where the randomness comes from? If we fit a model to our data, we get one residual per observation, right? That's only one value. We observe a value for EI. And then what is the randomness? What is the variance about? Any ideas?
It's a repeated sampling of the epsilon, right?
Yeah, it's the repeated sampling of the epsilon, exactly. So under the fixed design, yeah, this is very important to remember. Under the fixed design, the design matrix doesn't change. And the beta, even though we don't know it, it's assumed to be fixed under the frequentist paradigm. So then what's changing is the random sampling of the epsilon, the random error term. Once you get a different set of random error terms, you add it to the X beta, you get your response. So for that new data set, you fit a model, you have a new set of value for a new set of residuals. So as you repeat the random sampling, the residual I, since you know you fix the design matrix, so the ith observation is always there, but the residual will change. So that's why in the fixed design, it's very important that the hat matrix is fixed, it doesn't change. Sigma square is also assumed to be fixed but unknown. But given that the different observation will have different variance in its residual. And that variance is determined by the hat matrix, by the observation in the hat matrix. So we can give you some intuition for that. So you can see that some data points, some observations, if their predictor values are far away from the mean of predictor values across observation, then that point will have a large HII, and then its residual will have a small variance. What does that mean? It means that no matter how you repeat the sampling, but that point will stay close to the fitted line always. So its residual will stay as quite small, and it does not change that much. So that's what we call the leverage, and we'll talk about that very soon. But for now, let's talk about the HII in the special case, P equals 1. That's the simple linear model. Sorry, I should say P equals 2. I think that's a typo in the note. In fact, based on our notation, in simple linear model, we have one predictor, so P equals 2. So in that case, we can write down the H matrix, and it's a 2 by 2 H matrix. In that, it's still an n by n matrix. But since P equals 2, we can easily write it out, and then we can show that HII has this special form: 1 over n plus xi. Since here we have one predictor, so xi is a scalar, xi minus x bar squared summation. Let me see. Maybe I should say I prime go from 1 to n, xi prime minus x bar squared. That's the HII. And you can see that if given that the mean across observations stay the same as x bar, the farther away xi is from x bar, the larger the xii, and the smaller the variance of the residual. So what this means is that this is what we have for the simple linear model. And if we call this, right, then here is what we call x bar. And so for points farther away from x bar, their residuals will have smaller variances, but for the data points closer to that x bar, their residuals will have larger variances. And this is telling you that when we fit the line will be more driven by the points farther away from the mean than by the points close to the mean. So they have, for the points closer to the mean, they have less say on how the line goes. So that's why once you fit a line, for the points closer to the mean, their residuals will have larger variances, because sometimes their residual may be positive, sometimes it may be negative. So it's more uncertain. But for the farther away points, since they determine the line more, they can draw the line closer to themselves. So their residual will stay more unchanged across repeated sampling. Okay, that's it. And now realizing that the residual have different variances, right? You know, a standard check is to check whether the residuals will behave like normal distributions. So let's remember that this is the key thing. Epsilon I follows normal distribution with zero mean and constant variance sigma squared. But we don't observe epsilon I. We only observe EI, the residuals. If we want to use residuals as a surrogate for the error term, then there's an issue. The residuals do not have variance as sigma squared. It's actually multiplied by this specific term that depends on the observation I. So that's why it motivated us to talk about standardized residual instead of just the residual. So we can want to divide this part so that we can make the standardized residuals share the same variance. Okay, so standardized residuals. Let's call it SI. S stands for standardized. It's basically EI divided by standard deviation. And we know that sigma is unknown. We need to estimate it. So we will just use the estimate times the square root of 1 minus HII. So where's sigma square hat is what we estimated before. It's the residual sum squares divided by n minus p, the unbiased estimator we constructed before. So then, given that this one is normally distributed, and also given the given the law of large numbers, we will have this converge in probability to sigma squared as n goes large. In probability to sigma squared. So these can guarantee us to say that this thing is approximately, when sample size is large, standard normal distribution. So that's why you can check whether the standardized residual are well or are close to standard normal to run model diagnostics. This is a way to check whether the model assumption, which is this one, epsilon IID normal with common variance, is a reasonable model assumption. So this is the first thing, we do standardization. And this can also help you decide whether some residuals are unusually large so that you can call them outliers. So the rule of thumb, and this outlier is in terms of residual outliers. The residual is unusually large. The rule of thumb is to look at the absolute values of the standardized residuals and see if they are greater or equal than 2. And you can see where the 2 comes from. It's from the standard normal distribution. We know that for the standard normal distribution between -2 and +2, you have about 95% of your probabilities. So when they are greater than 2, it means that they fall into the tails, which together have only 5% of probability. So you think this residual is probably too large to be observed. So that's what we call the rule of thumb. Okay, so is the problem solved for in terms of this outlier exclusion? So you see there is a logic loophole here. That is, if you believe that the data may contain some outliers, then in your previous model fitting, to estimate the sigma square hat, to obtain this estimate sigma square hat, you already used those residuals. So sorry, you already used those outliers. And those outliers will affect your estimation for this variance term. So that's why a more reasonable way to think about this is that if I want to check whether observation I is an outlier, I should not include it in the estimation of the variance. So that comes to the term which we call Jackknifed residual. And I want to use this as the opportunity to introduce Jackknife. So Jackknife is a very useful statistical technique in the old times before Bootstrap became popular. So the idea of Jackknife is that if you have n data points, you will fit your model for n times, and each time just leaving out one observation. So this is very similar to cross-validation, the leave one out cross-validation. But we are more interested in, instead of a cross-validation for prediction, here Jackknife is used for parameter inference. So what it does is that if you want to check whether observation I is an outlier, you would not use it to fit a model to obtain sigma hat. Okay, so that is estimate sigma square from n-1 observation by excluding the ith observation, which is a potential outlier. Okay. So in other words, we can write down the Jackknife residual as EI. So same as here, but what's changed is the sigma hat. So now we use the sub-index with I in the parentheses. This is to mean that I is not used in the estimation. We excluded it. And this stays, this is fixed. Okay. So where I should say this, sigma square, this thing is defined as RSS. When we calculated residual sum squares, we excluded I, and accordingly, the number of observations is going down from n to n-1 minus p. That's how we calculate that sigma square hat I. Okay, so it seems that if you just look at the definition, it seems that you need to run n regressions by excluding one observation from each time. However, there is an interesting result derived by Weisberg in 1985, which allows you to have a direct one-to-one relationship between Jackknife residual and the standardized residual. So which means that it is sufficient to just run one regression so that you can convert a standardized residual to a Jackknife residual. And this is a very clear advantage of Jackknife in the old time. So when there was no computer. So let me write down this first. So in this relationship, you will just need to scale the standardized residual to obtain the Jackknife residual. Scale, and also here SI is also involved here. So the reason I say Jackknife is advantageous in that is because you know how it works. You only have a fixed way to calculate Jackknife residual. There's no randomness in your creating of the n-1 size samples. This is unlike Bootstrap. In Bootstrap, you're doing repeated sampling with replacement. So for example, if you have n observations and you want to do Bootstrap, every Bootstrap sample will still contain n observations with possible repeats. So what you do is that you usually set an upper limit for the number of Bootstrap to run. So every time, if you do not set a random C to be fixed, the Bootstrap samples may differ and the results may differ. But in Jackknife, you are doing subsampling with n-1 data points. So you have a total of n Jackknife samples. So you know what those n samples are. They are just fixed given your fixed data. And then you can calculate these in a deterministic way. So that's why Jackknife allows you to do some deterministic calculation. And this result is based on deterministic calculation. So that's why here, if you believe that, okay, Jackknife residual, so, okay, if you think from the logic point of view, Jackknife residual is more logically coherent than the standardized residual, because you would trust this estimation of the variance better. You are excluding a possible outlier in the calculation. So then you can use TI instead of SI, and you can still detect outliers based on the standardized residuals. But I would say that the difference is not so big. So that's why you see a lot of the diagnostics just use the standardized residuals. But I will just introduce the Jackknife for your knowledge. Okay, so that's it. And an equivalent way of interpreting the Jackknife residual is to think about what we call the predictive residual. Let me try to put this first. So then we will give you the equivalence between the two. So when we say predictor residual, we don't do this, we don't go this route. So there's two different routes. So the current route is that we fit one regression on all the n data points to get the residuals. And then we try to standardize the residuals in one of two ways. One is to just divide by sigma hat times square root of 1 minus h hat I. This is what we call standardized residual. For the Jackknife residual, what we change is that we replace sigma hat by sigma hat I. Okay, but still we're going from the route of fitting one regression to start with. While in the predictive residual, we are starting from Jackknife immediately. So this is defined as y minus yi minus y hat I. So what does this mean? So this is the ith observation, and this is the ith predicted response by excluding I. By excluding the ith observation in model fitting. So which means that we are fitting a model based on the other n-1 observation and apply that model to the ith observation to do the prediction. And then we calculate the difference. This is what we call the predictive residual using the Jackknife. Okay, so one interesting thing to see is what is the variance of this predictive residual. And we can do the calculation quite easily now. The reason is these two things are independent. So why are they independent? This is the question for you to think about. Here, the randomness of yi comes from epsilon I. But since yi is not used in the model fitting, so the fitted parameters have no randomness related to I. Their randomness only come from the other n-1 observation. So that's why if we apply that beta hat, maybe I should write this out and you can see that better. So this is yi minus xi transpose the ith row in the design matrix times beta hat I. So you see this row is fixed because we are doing a fixed design. And the randomness is coming from that beta hat, which is only dependent on the other n-1 observation. And while the randomness of here is from epsilon I. Since those epsilons are independent, we know that this and this, they are independent. That's why these two things are independent. And this is very important for our calculation of this variance. So because of independence, we can write as the variance of yi plus the variance of this yi hat. Okay, and clearly the first term is sigma squared. And for the second term, we're going to use this. So you can see that this is what? This is, for the second term, we need to use the least square formula for this beta hat I. So let's keep the ith row here. And that ordinary least square in that formula, the design matrix need to have the ith row deleted, right? So to compute this. And we can write that as xi. This means that we have the ith row removed, transpose xi inverse times xi transpose yi. So I remove ith observation from this formula. And then, because this part is considered as fixed, the only randomness is in the y sub I. That's the n-1 observation. And then what we can do is that we can use that variance formula to move this out. and take the variance covariance matrix of this n-1 vector, and also right multiplied by the transpose of this part, right? So finally, we will be able to see that this is just equal to, after some simplification, this is just equal to first term stays, the second term is sigma squared times xi transpose xi transpose xi inverse times xi. Okay, so here these two things are the ith row, and this is the design matrix with the ith row deleted. So we will have this formula for this predictive residual, which is taking us the difference between the actual response and the predicted response without using the ith observation. Okay, so why do we want to talk about this? The reason is that now we can see a very interesting equivalence relationship. That is, this Jackknife residual can also be shown to be equal to this, yi minus y hat I divided by this. I put a hat here. So in other words, you can consider the Jackknife residual to be the standardized predictive residual. It's for your interpretation. So if I make it more explicit, it's this. Here the hat needs to get out. So basically the hat involves sigma hat. So it's sigma hat I get this out times 1 plus this term xi transpose okay. So this is exactly what we mean. Okay, so finally, this is the introduction for the Jackknife residual. And as I said, for the rule of thumb, you can apply it to the Jackknife residual. So that is check the TI greater or equal than 2. That's also a way for you to decide whether there are outliers. And also you can apply the normality check to the TIs to see if they are approximately normal. Okay, and yeah.
Sorry to interrupt. In the denominator on the right for TI, is it sigma squared hat excluding the ith observation, or is it? I was.
It's the sigma squared excluding the ith observation. Yes.
Okay, I was just wondering, how does that follow from the variance derivation in the line above that?
So we're just plugging the variance here, right? And then because the sigma square is unknown, we need to give it an estimate. That's it.
Okay. So I just didn't see how it follows that it excludes the ith observation.
No, in the variance, there's no exclusion. It's just that when we try to write down the standardized predictor residual, we must plug in an estimator to replace it. Otherwise, it's not computable. So that's why here you see I put a hat above the variance. Yeah.
Okay, thank you.
Okay, so a final way to understand this residual or this Jackknife residual or what we wrote here is to think about it from a more formal regression framework. So I think this is something good to think about. Maybe this can motivate you to think more about the use of statistical modeling to answer your specific question. So we can actually think about a test for outliers. So if the question is whether we think the ith observation is, or which I should say, whether we think the jth observation is an outlier, okay? So is the, maybe I should stick with I. Let me think. Probably, okay, let's just say this. Is the I star, I call this observation, an outlier? Okay, if I want to ask this question, then among our n observations, we are only interested in one observation and we want to check whether it's an outlier or not. So to answer this question, we can introduce a binary indicator predictor into our model. So we can introduce Zi as our binary indicator, and we give it two values. It's just this. It's an indicator whether I equals I star. So in other words, we have Zi equal to 1 if we are talking about the I star observation, and 0 otherwise. So if we think about this, then we can write down our model. The systematic structure of our model can be written as mu I, which is the expectation of yi, just as a reminder, is equal to xi transpose beta, the linear part. This includes the intercept, plus gamma times zi. We can write it this way. So you see that if we write the model in this, we're basically checking whether the ith observation has a different intercept, and that intercept is offset by gamma. So this is equivalent to say that I have mu I star equal to xi star transpose beta plus gamma and offset. And for the other observations, I just have the linear term. So this can specifically make our attention to gamma, right? Then we're translating the outlier detection problem to testing whether gamma is 0. And we know that we can try to do t-test to answer this question, because now gamma becomes one parameter in our linear model. And the corresponding design matrix, the new design matrix, is just our, or maybe I should put it away, it's just our original design matrix, x1 transpose to xn transpose, with an additional column corresponding to the binary indicator. So that is, we can put z1 to zn, right? And we know that in this column, only one entry is 1. xi transpose, xi star transpose to xn transpose, 0, 1, 0. So this is the ith observation. So when you have one entry as 1 in the design matrix, then we can run the linear regression. But just one thing to be certain about the slope estimation is that if we want to have the correspondence between this approach with the Jackknife-based approach, okay? So if we want to show that the t statistic, okay, the t statistic is just gamma hat, the estimate divided by square root of its estimated variance. So if we want to have any correspondence between this and the previous Jackknife residual, a key is that when we estimate beta, we should only use n-1 observation by excluding this xi star from the estimation to estimate beta. When we do that, then we can have some equivalence. But if we just run standard linear regression to estimate this beta together with gamma, then we are going to use all the n observation for our beta estimate. So that's just one small thing to note. And the detail of this is in my lecture notes. So I'll just quickly write this as, this is equivalent to the TI jackknife residual, or TI star, I should say TI star, the jackknife residual, if beta hat is okay, I should say if beta hat is said to be beta hat with the I stars observation excluded. Okay, so that's all. So I think to just summarize what has been said so far is that in the diagnostics of linear regression, the key is to look at residuals. The key is to look at the residuals. But one thing we need to keep in mind is that not all residuals have the same variance. This is their key difference from the random error term. So to account for that fact, we need to standardize the residuals before checking whether they together can be fit by a Gaussian distribution or they approximately follow a normal distribution. So in the standardization, we need to involve the unknown term sigma squared, sigma. So since we don't know it, we must replace it by sigma hat. Then the key question is, how do we find sigma hat? The simple way is just to use the sigma hat obtained from our regression. If you believe there's no outliers, you're good. But if you believe there are potential outliers and you want to use residuals to rule out those outliers, then you don't want to include outliers into your estimation of sigma. That's why we are motivated to do the jackknife residual. That means to check whether the ith observation is an outlier, we don't include it in the variance estimation. And that's here. And a parallel thinking is to use the so-called predictive residual. That is, we are not thinking about standardization from the regression that's fit to all data. We consider for every observation, we try to predict it by not using it in the model fitting. That's how we do here. And here, after we obtain the residual, we calculate its variance, and we found that this variance is also dependent on the value xi itself and other values. And of course, it's also involving sigma squared, which is unknown. So we still need to find an estimate to plug in. So we can show that these two approaches are equivalent. And the third approach, which is more model-driven, is to formally test whether a particular observation is an outlier. To do this, and then you can run the t-test. But one thing I want to say is that it's something good to know, especially for our PhD student, and this is currently a very important research area in statistics, is that when we want to say whether the I star observation is an outlier, this I star should not be picked by data. This should be something you pre-specify and then you test it. If you look at the residual already, then you zoom in and found this I star, and then you test it again. Basically, you use your data for twice. So this is something as a statistics student or PhD student, you should have that caution in your mind. So in many cases, we do not have a very good solution, to be honest with you guys. So we have to just make conditional arguments to say, okay, conditioning on this data being fixed, we do blah, blah, blah. But if we want to make the whole thing rigorous, we need to think about, okay, if we use the data for twice, we may need to do some adjustment to make the inference valid. Okay, so that's all for the residual part. One more thing I want to say, which is in the lecture notes, is about the multiple testing correction. So that's related to testing for outliers. Let's say we have n data points and we run an outlier test. If we do that for every data point, then you're going to do n tests. And if n is quite large, you need to consider multiple testing correction. So I would say that this is not so much of an issue nowadays because usually your data points are so many, the n is very large. So in many cases, people do not really care if some data points are left out. In other words, the data points are becoming cheaper. So you can leave out some potential outliers without too much worry. But in the old days, if your n is very small, you need to be very cautious when you want to leave out a data point or throw out some data points. So that's why you are very concerned about the false positives. That is, you make a false outlier call. You want to reduce that number of false positives. So that's why there were some multiple testing correction, and the Bufferonic correction is the most conservative way. That means you are very unlikely to call a data point outlier unless you have a very, very strong evidence. So Bufferonic correction is basically you divide your significance level, say 5%, by the number of tests. And only if your p-value is less than that, alpha over n, you are going to reject it. Otherwise, you do not reject. But that's very conservative, as you can see. So you are not going to reject a lot of small p-values after the correction. So if you're interested in this part, you can check the notes for that Bufferonic correction discussion. But as I said, for n relatively large, this is not so important. Okay, so finally, before we conclude this part, we're going to talk about some other aspects, which is some other ways of defining potential outliers. So here, the outliers defined based on residuals, right? But there are two other ways we can think of the influence of a particular data point on the result. So the first one is what we call the leverage. And the leverage is indicating potential influence of an observation on line fitting. So from our residual variance, we already see that this is just HII. So the larger the HII, the smaller the variance, right? So we know that if HII goes up, then the variance of residual I will go down. So we know that HII has a potential influence on the line fitting. And how do we, so basically we need to be quite cautious on those data points. They are not necessarily bad, but we want to make sure that their measurements, that if a data point has a very large leverage based on its design matrix, so this is determined by this design matrix, okay? Determined by design matrix. If given the design matrix, one data point has large HII, we want to check if you think the measurement of YI is trustworthy. This is very important because we know that if we include this data point into our regression, it will have a large potential effect on the model. So if it's accurate, then of course it's good to use it, right? It can help you fit a reasonable line. But if YI is questionable, especially I think in some biomedical data, some measurements, if you check it, especially if the HII or if the just in the simple linear model case, if your XI is very small, which means that it's on the very left side of the mean, then you may check whether the measurement is accurate, because for those low measurements, it's possible that this is not so trustworthy. So you want to account for that before fitting your model. Okay, so how do we think of a leverage is large or small? So we think of the trace of H. So trace of H, if you recall, is the summation of HII. And we know this is equal to P, right? So the total leverage is P. So here is another rule of thumb for practical consideration. Is to check if HII is greater than 2 times P over N. So what's the rationale behind this? This is what we think of as the average leverage across data points, right? P divided by N. And if this is larger than twice the average, we think this is large. Okay, that's the leverage. And the last thing we want to discuss is what we call the Cook's distance. You are going to see both the leverage and Cook's distance if you run the regression diagnostics in R. So for example, you can check this if you do plot like LM, Y, X, something like this. Then R will output a set of plots, including all the information we discussed here. So the Cook's distance is what we call the actual influence. So it's not just potential, it's the actual. So what's the difference? For the potential influence, it's only using X. So this is only dependent on the design matrix. But here, the actual influence is using both X and Y. So you look at the whole data set, you run the regression, and you know what's the actual influence. So for this one, when you're only using X, you're no regression is done at all. You're just inspecting the design matrix to inspect the potential influence. So that's the H, has nothing to do with Y. Okay, so for Cook's distance, it's defined as this. So you can think of it as the change in your parameter estimation. So let me write down this first. It's defined as DI, which is written as beta hat I, which means you excluded I from the estimation minus beta hat. This is what you have by including all the observation in the estimation. Okay, you want to look at this, but you are looking at its square form, so you do not have a sign. And you want to also normalize that square difference by variance. So here we are basically doing this variance hat of beta hat inverse. Sorry, I have this transpose times beta hat I minus beta hat. Okay, and you divide this by P. P is the number of predictors. That's the Cook's distance. So you see, this is like the walled test statistic for what? This is very similar to the walled test of null hypothesis that beta equals beta hat I. So in other words, we are treating this beta hat I to be fixed, right? Because we know in hypothesis testing, we cannot set a hypothesis with a random parameter there. So here we're assuming this to be fixed. So we are testing whether our beta equals this thing. And so that's why this is just a wall test statistic, similar to the wall test W divided by P. So in wall test, there's no division of P, but here we have the division of P. So that's the Cook distance. It's just a way to quantify the change in the slope estimate as you remove data point I. So that's about the actual influence. And here we have also a rule of thumb that's also based on this distribution of this wall test, if you recall. So we have the wall test W follows F distribution with P and N minus P degrees of freedom. So based on that distribution, we derive a rule of thumb for checking the Cook's distance, whether it's too big to be worried about, that is 1. So that 1 is actually the median of that F distribution once we divide by P, of course. So this W has a F distribution, and we take that median that's close to P, and that median divided by P gives us 1. So that's how we check whether Cook's distance is large or small. So I would suggest that you play with this in the R function, and then you can see that you will be able to see in some cases, you will see there are some outliers there. Okay, so I guess that's all for today about this diagnostics. And next time when we come back, we will just do some very quick introduction for normality check. If you want to check whether the residuals follow normal distribution, we use the QQ plot and what that actually means. Many people use it, but many people are not so clear about what it means. And then lastly, we're going to talk about Box-Cox transformation in linear regression. That means if the data do not fit a linear model well, you may consider to transform your response to make the linear model reasonable. Okay, so I'll see you on Thursday. And for those of you who want to stay in the Zoom, just let me know. I can let you guys